Have you ever stopped and wondered how we power an entire country? I mean, really power it. It all comes down to the power grid, this absolutely colossal machine. Today, we're going to pull back the curtain on this special, kind of secret language that engineers created to understand and control this beast. So let's dive right in.
Just look at this thing. The power grid, it's just this incredible, dizzying maze of power plants, transmission lines, and substations. It's not a bunch of separate pieces. It's one single, massive system where every single part has to work in perfect, beautiful sync.
So that's the big question, isn't it? How can anyone, possibly wrap their head around this whole thing at once? How do you manage the flow of energy in a system that's just so massive and complicated?
Well, to even begin to tackle this, engineers had to get really clever. They started thinking about the entire grid as one giant electric machine. But, to actually understand it, they needed a completely new way of looking at it.
And the answer, it turns out, is a classic engineering trick: modeling. The idea is, instead of trying to wrestle with the messy, complicated reality of the whole thing, you create simplified mathematical versions, models, of each individual part. You understand the parts to understand the whole.
All right, so let's do just that. We'll start right where the power is born, inside the power generator. You can really think of this as the heart of the entire grid. It's the source of all that electrical energy.
Okay, so the technical name for this thing is a synchronous generator, but you can just think of it as a giant alternator, kind of like the one in your car, but, way bigger. Its whole job is to take the spinning force from a turbine and turn it into the three-phase power that, runs our entire world. Now, this is where it gets really fascinating. Look at how engineers simplify this incredibly complex machine. On the left, you've got the real deal, right? And on the right, you have its model, what's called an equivalent circuit. All of that complicated physics gets boiled down to just a voltage source and something called impedance. Impedance is really just a fancy word for how much the circuit pushes back against the current. It's an absolutely brilliant simplification.
Okay, let's move on to the next piece of the puzzle. We need to talk about the unsung heroes of the power grid: transformers. They don't actually make any power, but believe me, the system would completely fall apart without them.
Think of transformers as the on-ramps and off-ramps for the grid's electrical highways. They step up the voltage to these crazy high levels so it can travel efficiently for hundreds of miles with minimal loss. Then, at the other end, they step it down so it's safe enough to actually use in our homes and businesses.
And here we go again. This is just a perfect example of that consistent modeling strategy. Just like that giant generator, this huge, heavy, oil-filled transformer gets boiled down to another neat little equivalent circuit. It's what allows engineers to predict exactly how it's going to behave with math without getting bogged down in all the messy physical details.
Okay, but this whole strategy creates a new problem. You see, a big generator might be rated for, say, 90 million volt amps at 22,000 volts. But then a motor way down the line is rated for totally different numbers. Trying to analyze them together, it's literally like trying to compare apples and oranges. The units, the numbers, they just don't line up at all.
So what do? Engineers needed a solution, and fast. They needed a universal translator, a way to make all these different components with all their wildly different ratings speak the exact same mathematical language.
And the solution they came up with is something called the per-unit system. It's this incredibly clever idea where you express all the different values, voltage, current, power, you name it, as just a simple fraction of some common starting point, a base value.
It's actually super simple when you break it down. The per unit value is just the real value of something divided by that base value you chose. You can think of it just like a percentage, but written as a decimal. So instead of saying 50%, you'd say 0.5 per unit. That's it.
So why is this such a game changer? Well, for one, it standardizes everything. Suddenly, that generator's voltage and that motor's voltage can be compared directly, apples to apples. It makes the math way simpler, it helps engineers spot potential problems from a mile away, and it's absolutely perfect for the complex computer simulations that run the modern grid. And this isn't just some textbook theory. This is how engineers actually predict stress on the system and prevent those massive cascading blackouts.
Okay, so now we get to the big payoff. We have our common language. So now we can finally zoom back out and look at the entire system as one single understandable thing. Remember this? This is where we started. This incredibly complex diagram, where every single component was speaking its own language of volts and amps and ohms. It was just a total mess of numbers that didn't work together.
But now, watch what happens when we apply that common language, the per-unit system, to every single one of those components.
And we get this. All that complexity, it just vanishes. Everything is translated into a single, clean, elegant diagram, where every value is now in per unit. It's not just nice to look at, it's a circuit that engineers can actually solve.
And that right there is the ultimate goal of all this modeling. By creating this abstract layer, this common language, engineers can take a physical system that seems impossibly complex and turn it into a mathematical problem that they can actually solve.
Which really leaves us with a pretty fascinating thought, doesn't it? This whole idea of creating a common language is what allowed us to tame the power grid. So you have to wonder, what other ridiculously complex systems, things like our economy or even our own biology, what could we unlock if we just found the right language to describe them?